And then we have to ask how many objects are there in each case. 2 objects on the left, so 2 terms on the left, 1 object on the right. So you always have to ask how many objects there are in each situation when you're doing a collision. Because in a collision, the number of objects can change if they stick to each other. And here we saw this is the momentum of object 1. One of the momentums was 0. Once they're together, they have a combined mass, and then we solved for V3. All right, so now we've done 2 different questions. So how did we know to use conservation of energy for the first problem and conservation of momentum for the second? Well, the second was a collision. So that was a good case to use conservation of momentum. The first one wasn't really a collision. It was just a single object going from one place to another. Well, that tends to be when you want to use conservation of energy. So you need to have to think about that. Okay. All right, so I can erase this. So again, on the test, so in a way, we've been kind of giving hints here. On the test, they might have just left this question out. On the test, they might have left this question out and just asked you, what would be the speed of the combined object after the collision? Right? They might have just said, A starts at the top, it goes to the bottom, and then it collides with B and sticks with it. What's the speed of the combined object after the collision? And then we have to have enough physics sophistication to see that that's really 2 separate problems. First, we have to figure out what the speed of A is at the bottom. That would be our sub-question. And only then can we actually figure out the speed after the collision. So we have to see this is really first a conservation of energy problem and then a conservation of momentum. And again, it's almost guaranteed you'll see a problem like this on the exam, a problem that combines both conservation of energy and conservation of momentum. Almost for sure, you'll see at least one question like this. So sometimes you have to look at a problem and say, aha, this problem is actually split into subparts. I have to split this into subparts where I use energy on one part and momentum on another part. Okay, so that would give us this. Does that make any sense? Okay, and even this is maybe a little bit easier than you would see on the test. Let's put in one more complication. So now we have object C, which is attached to a spring. All right, object C here attached to a spring, and it has a mass of 2m. And let's say that it also has glue on the side. So when anything touches this, again, it'll stick. So again, everything's going to stick to everything else here. So what we're going to have now is we're going to have the combined A and B object that's going to hit object C. So let's figure out what's going to be the speed of A, B, and C right after that collision. So the new question is, the speed of the ABC object immediately after the collision. And we'll keep assuming there's no friction on the surface. So there's not going to be any friction here that slows things down.
So is it when the object is colliding into the spring? Well, it's going to be stuck to it, so it's the action of going towards the end of the, that's what we're finding?
Let's see. So we're going to be asking what happens the instant after A and B have collided with C. So once they've collided, then obviously the spring is going to start to contract. But we're not going to worry yet about all that contraction. We're just going to talk about the first instant when it's first started contracting. We want to know how fast is the spring contracting originally.
Okay.
Is that clear? I don't know if I explained that right. Okay, good. Okay, so what would be our general approach for this?
Well, we would start by using the same kind of process, right? So P initial equals P final.
Right. That's right. It's another conservation of momentum problem because it's another collision. Maybe we can call that now net momentum 3, no, net momentum, yeah, 3 equals net momentum 4. Because we already figured out situation 3, the speed of the AB object here, and now we're going to have situation 4 when we have the A, B, and C combined. Okay. All right, so now we'll have to start plugging in there.
So, net momentum is MV is
Mm-hmm.
3 before, and so the massive is 2m, right?
Good.
Times the V3 that we found earlier, which is square root of 2gh over 2.
Good. So momentum is m times v. So here's the mass of the combined object of A and B, and we already figured out what their speed was going to be here. Okay, good.
Would these twos cancel out each other, or should I just leave it like that?
You're right, they would. That's right. You can cancel these twos.
So then the mass of all three objects would be 2m plus 2m,
Good.
so 4m.
That's right. So together, after the collision now, we're going to have a mass of 4m.
And we want to find the v, so it's v4.
That's right. We don't know what v4 is. That was the whole question. So we just plug in a variable for that.
Where does the spring come in?
So far, it hasn't come in.
Okay.
And the reason it hasn't come in yet is because we want to know the speed immediately after the collision. Well, immediately after the collision, the spring has only just started contracting. So there isn't going to be really much impact from the spring yet.
Okay.
So far, this is just momentum problem.
So then it's m times 2gh divided by 4m.
Right.
So that equals square root of 2gh over 4.
Like this?
Yes.
Okay. Okay, good. That's good. All right, so we did another collision here, and now we found the speed v4. Okay, does that make sense? All right.